Let's look at the technique of linear regression for performing regression. So again, I'm making a distinction between the generic term regression, which is any model that can make a numerical prediction, that's called as a regression model, and linear regression is a particular technique for regression. We'll be looking at other techniques for regression as well. Now, sometimes people tend to think about regression and linear regression as synonymous. That is really not the case. Regression is whenever you're making a numerical prediction. Linear regression is a particular technique which does that. So a predictive model, as we've already seen, is basically a way to calculate a predicted value for a target attribute based on values of the predictor attributes. Right? That's what a model is. It gives you, given the values of the predicted of the predictor attributes, it gives you a way of computing a value for the target attribute. And of course, we know that the process of machine learning works in this way. So we have historical data. We feed this historical data to a computer. The computer, looking at the historical data, builds a model, builds a mechanism for making the prediction, right? And that's the predictive model. We then take that model and apply it to future cases. That's what we've been doing up to now. And when it came to classification trees, our model was a tree, right? So based on the historical data, the computer figured out a tree. We are then able to take that tree and apply it to future situations. So your model is the tree itself. In the case of KNN for classification, we already saw that our model is the combination of the training A partition or a data set plus a value, a preferred or chosen value for K. So now when we have to classify a future case, we take the future case, find its K nearest neighbors in the data set and make a prediction according to that. Okay, so in K nearest neighbors, that was our model. In the case of naive Bayes, our model was just a bunch of conditional probabilities. And using the conditional probabilities, the system is able to generate an approximation for the probability that we are seeking, probability of a case belonging to a particular class. Okay, so now the question is, in the case of linear regression, what does the model look like? Okay, so all we are doing in all of these cases is finding some way of computing the value for the target attribute based on values of the predictor attributes. And we've seen several classification examples where we have done that. The first regression technique we are looking at is linear regression. And what does a model look like in the case of linear regression? Let's take a concrete example. Let's say that a family is going out on vacation, and let's say they're going to stay at a particular resort, and the resort is interested in finding out an estimate or predicting how much money this family is going to spend when they stay at the resort. Okay, so it's possible that the amount of money that a family spends during a vacation at a resort depends upon their annual income, the number of days they spend at the resort, obviously, the location of the resort itself. Some resorts are more expensive than others and so on. So obviously the amount of money you spend is going to be different, depend on that. And perhaps it also depends upon how far away from home you have traveled, right? So for example, if this is a very special location for you, you have traveled very far from home to come to this location, then it is possible that you may end up spending more money at this location. And we can think of many other attributes that will determine how much money a family is going to spend on the vacation. Okay, so these are all your predictor attributes, and that's your target attribute. And of course, because we are talking of machine learning, the way in which the system is going to build the model is by using historical data applicable to this context. Okay, and of course, all of this talks about the relationships between all of these attributes to the target attribute. Okay, so now what we are going to do in linear regression is to compute a formula. Like, don't worry, get phased by the Greek symbols. It's just traditional to use Greek symbols for these. So we are just saying that the amount of spending, and notice here there's a hat on top of spending, which means what? Which means that it is our estimated value for spending or the predicted value for spending. You put a hat on top of it just to distinguish it between from the actual spending that took place. Right? After all, when we are using historical data, the historical data contains the actual amount of money that was spent. Okay, we want to distinguish that from the predicted amount of money. So it's common practice in statistics and mathematics to put a hat on top of predicted or estimated values. Okay, so we are saying that the amount of money that a family spends is dependent upon the income, the number of days they are spending at the resort, how far away they are from home, the distance, and the location of the resort. Right? In linear regression, what we try to do is to create an equation of this sort, right? Where beta 0 is some number, beta 1 is some number, 2, 3, 4, they're all some numbers. And it is the job of the model, of the linear regression model, to find out what these numbers are. Okay, so once it finds out what these numbers are, for example, beta 0, let's say is 100, beta 1 is 25, beta 2 is 3.45, beta 3 is minus 23, and beta 4 is 2.68. Some four numbers it figures out, right? Then it's telling you that in order to calculate an estimated spending, plug in those values of beta 1, beta 0, 1, 2, 3, 4, and take the actual values of income, the predictor attributes, multiply them and compute this expression, and that is going to be the predicted spending. Okay, this is what we are trying to do in linear regression, right? So therefore, in linear regression, our model is just a linear equation which looks like this. Okay, so once again, the Greek letters that we are using here, basically the beta, it's just convention. We could have called it X or Y or A or B, but it's just convention to use the letter beta in linear regression. It just stands for a number. Okay, and these are the numbers that the system will try to find out. It will use the historical data and figure out these numbers. We'll talk more about it shortly. Okay, so that's your regression equation. Okay, so this is the hat on top, that's what they call it, hat, and this is spending hat, which is a predicted spending or estimated spending. Okay, the first coefficient beta 0 is called as the intercept, and shortly you'll see why they call it the intercept. Okay, and beta 1 is the coefficient for income. These are called the regression coefficients. All the betas are called the regression coefficients. Beta 0 is the intercept, and beta 1, 2, 3, 4 are the regression coefficients for the various predictor attributes that we are using. Okay, so that's just terminology for regression. Okay, why do we call this a linear regression? Okay, after all, beta 1 times income, beta 2 times days, they're all, there's multiplication going on. Why do you still call it linear regression? The reason we call it linear regression is that this is an equation in each of the predictor attributes raised only to the first power, right? So for example, we don't have an income squared or a distance cubed. We could have those, but in linear regression, we don't raise any of the predictors to any power other than 1. Okay, that's why you call it as linear regression. We can write the regression equation in two ways. The first way is what we just saw, where we say spending hat is beta 0 plus beta 1 times income, etc., etc. Or we could write it in a slightly different way. You can write it as spending equals all of these terms plus an error term, or what is called as a residual term, right? So because in this equation, we don't know the actual value of spending, right? So we are saying this is the estimated value. So naturally, the question arises, well, what is the difference between the actual value and the estimated value? To get a better idea of that, you can write your regression equation like this also, right? So this is the computed estimated value plus an error term, which gives the actual value. Okay, so the error term is nothing but the difference between the actual value and the estimated value. That's just another way to write it. In this course, we will uh, content ourselves in writing the regression equation like this, but it's quite possible you may see this as well somewhere else. Okay, this term is called as the residual, and sometimes we also refer to it as the error because it's the difference between the actual value and the predicted value. But in the field of statistics, people don't like to think of this as an error. They like to think of it as more as a residual, and we'll see why they call it the residual. Okay, so why do we content ourselves with just building a linear model? Why not build a nonlinear model where some of the predictors are raised to different powers? For example, you may have one predictor raised to the half power, which means taking the square root, another predictor raised to the second power, a third predictor raised to the 2.5th power. You could have any of those things, right? You could build what are called as nonlinear regression models. You can do that, and sometimes it's appropriate to build nonlinear regression models. It's just that you can get more and more fancy with the kind of modeling you do. And sometimes what happens is that as you build your model, make your model more and more complex, it's again runs into the same problem of overfitting that we were talking about. Okay, there is also a historical reason why we talk about linear regression and not other forms, other powers of regression, because there is a history to this, that people have been doing regression for quite a long time. In fact, I think the linear regression as we know it was probably invented by Gauss, so it's quite old, and therefore, just historically, it was not possible for people to do other kinds of regression because of the amount of computation that was involved. Okay, with linear regression, the amount of computation was reasonable, and therefore that is all they could do by hand. Okay, so it is also for this reason that linear regression continues to wield power even today. And in the field of social science, linear regression is used quite a lot. And sometimes people tend to think that that's the only correct way to do things, which is of course not the case. And if you find in a situation that you build a nonlinear regression model and that works well for large amounts of data and it's quite stable, then why not use that? Because today building a nonlinear regression model is not all that difficult. Okay, but in this course we won't be talking about nonlinear regression models, but I just want to give you an idea of the fact that they exist. Okay, of course, when you look at a linear regression model, you can eyeball linear relationships with scatter plot when you have one predictor and one target, right? Of course, if it goes beyond that, then you cannot visualize it. So in this case, I've just taken our good old Boston housing data, and here we've got the average number of rooms in a neighborhood and the median value of a household in that neighborhood. Okay, and clearly you can see that there is a kind of a linear relationship between the two. Obviously, the relationship is nowhere near perfect, because if it was perfect, then you would have all the points lying on a precise straight line. That's not happening. On the other hand, you do see that there is a trend. Okay, first of all, you expect the median value of a house in a particular neighborhood to be higher as the number of rooms increases. That's exactly what you're seeing here. Okay, so there is clearly a well-defined trend, but it's not exact, right? So there are homes with more rooms which have lower prices. So for example, if you take this house here, it has fewer rooms than, let's say, this house. This house has more rooms, but this house, this neighborhood, I'm sorry, not house, this neighborhood's median value is lower than the median value of houses in that neighborhood, which in general have smaller number of rooms. Okay, that is possible. So we are not saying this is exact, but in general, there is a trend. That's all linear regression is going to tell you, right? So again, going back to the same idea that we've been talking about quite a lot, just because we are building predictive models, we should not get carried away and think that these models are going to be fantastic in terms of prediction. Okay, all we are looking for is what can we do without the model? How much are we able to improve things with the model? Okay, and even if that improvement is quite small, it may still be significant. That's the mindset that we have to take.